We'll continue now with the second part of the introduction to biostatistical consulting and applied problems. We'll start with reviewing the 4 phases. So again, phase 1, state the question. Phase 2, decide how to answer the question. Phase 3, answering the question. And phase 4, communicating the answer to the question. So if you recall phases 1 through 3, the first phase, steps 1, 2, and 3, look at evaluating and describing your data, reviewing your general assumptions, and then stating the question in statistical terms. Phase 2 is steps 4, 5, and 6. So choosing your summary statistic based on your statistical question. How does random variation affect that observed statistic? So what would you expect to see under the null hypothesis? And then step 6 is your decision rule. So how will you choose between your null and alternative? And then phase 3 is actually answering the question. So again, it's not until you get till step 7 where you actually do the analysis. And again, I can't stress enough that you shouldn't skip steps 1 through 6. That's when you get in trouble. So then once you get to step 7, you can calculate the statistic or fit the model. And again, if you're fitting a model, you're going to jump back and forth between step 7 and step 2 about reviewing the assumptions that are associated with those models. You may have to jump back to step 2 if you're trying to decide, say, between a t-test and a Wilcoxon or between a chi-square and a Fisher's exact. So you'll check the model or test specific assumptions in step 7. In step 8, you'll make your statistical decision, so that will choose between your null and alternative hypothesis. And then step 9 will be stating your substantive conclusion in words, or putting it back in the context. So let's go ahead then and wrap it around to phase 4, which is communicating the answer to the question. And so this is, again, really key. This is very important. It's to communicate what you understand the results to mean. So again, the p-value is not the answer. The p-value is how you make your decision. The answer to the question needs to be put back in the words of your data. So you formalized a question, you've described how to answer it, you brought the data to bear on the question, now you've answered it, and step 10 is going to wrap all of that into text, tables, and figures to be able to relay this information back to the appropriate audience in terms that they can understand. So we'll start with an example here. This is looking at multiple sclerosis specific healthcare utilization. So wanting to look at doctors that treat MS or a neurologist that treats MS, visits to have a brain MRI, and then looking at that by relapse activity, disability status, and participant characteristics. It would be very difficult to answer these questions if you don't keep track of your progress, data sets, and results. And again, if you're looking at all of this in context, you don't want to have to investigate the data each time you try to answer one of these questions. So you want to start in step 1 with making the decisions that will have you end up with a data set that you use to address all of the questions. So you'll start about listing out how the data are included in the time frames. So for this case, it was 2015 from October to December, collected online or via mail. So this is self-reported data, which means we won't be able to go back and fix anything that we think is potentially wrong. So because this was self-reported within a specific time frame, if there's an answer that's absolutely incorrect, then we'll ultimately have to delete that observation. Because we can't go back and ask somebody in, say, January 2016 how they were feeling in October 2015. Participants were asked about their MS status in the prior 6 months. And those were defined as relapse symptoms, which were categorical, yes, no, or unsure. Disease progression, again, yes, no, or unsure. Their most recent visit to their multiple sclerosis doctor or neurologist, and their last MRI, and that was also categorical in the categories as shown here. And then current MS disease course, and again, self-report under these categories. So we were really looking at categorical descriptive outcomes here in a self-report data set. We wanted to start with the distribution of each variables and record any data cleaning. So did we have to change anything? Did we have to remove anything? Were there any duplicates? So sometimes people can mail in 2 surveys. It's hard for that to happen in our comms, but it's possible. Or it happened to get entered twice by mistake. And then what were the reasons for any of that data cleaning? The N and the N missing are really critical here because we might start with 12,000 and end up with an analysis set of 8,000. And then what's the final N for analysis? And these two last points are commonly missed on the qualifying exam. Because you've been given the data, oftentimes students forget to reflect back what that data means. And so it's really key to remember, if you've done any cleaning, what is the N you started with and what is the N you ended up with, and then any of the decisions that you made. One way to help is with the consorter's strobe statement. These are really great statements that you can use. They deal with how you report data in a manuscript, and so it will help you, if you look at them when you're trying to do the analysis, to remember what things are required to be reported so that you don't forget those steps as well. This is an example of what's generally called a consort diagram, or it could be the strobe diagram. But basically you can see that we had 7,648 fall responders. 24 of them were missing all of the inclusion criteria. Another 784 were missing at least one of the inclusion criteria, so the responders did not answer those questions, which means we can't use them. So we need to then exclude them, and you can see here how many were missing MRI, relapse, neurologist, or MS type, and therefore we had 6,840 that were included for analysis. So we wanted to start with the distribution of each variable, record the N per variable, the mean, standard deviation, standard error, or proportion. If you were dealing with continuous variables and you were in smaller sample sizes or very skewed data, you might be reporting medians and interquartile ranges. And remember that standard deviation describes your sample, and standard error describes the confidence about your mean. So in your so-called table 1 that describes your sample, you should always use standard deviations. Do not report a median, IQR, a mean, and a standard deviation and a standard error all in the same table for the same variable. That basically means that you're leaving the interpretation of the distribution of the data up to the reader, and that should be your job. So if you're going to be doing median tests, report the median. If you're going to be doing mean tests, report the mean. Look at the distributions of the continuous variables, look for errors and outliers, look at counts per cell in categorical variables, also very key. That will help you determine if you have sparse data, which could then, particularly if you're getting into interactions, cause problems in your models. You want to start first with preliminary analysis, so fit all your X by X. This is how you'll look out for collinearity with continuous variables or categorical confounding. So if you have two continuous, this is going to be basically a correlation or a Spearman's. If you have two categorical, you're looking at a Fisher's exact or a chi-square test. And if you have continuous and categorical, because you're looking at two predictors, it's really easier if you look at a t-test or a NOVA. So compare the medians or means across the groups. And really what you're looking for here are significantly strong relationships that could possibly cause a problem in a model together. So something like age of onset of symptoms and age of diagnosis are very closely related in a lot of diseases, and you wouldn't want to use both of them in a model. So this can help you sort of eliminate or be aware of potential issues in modeling. And then you for sure want to fit all X by Y in univariate unadjusted relationships and record all those relationships. This may be the end of your analysis if it's a simple univariate analysis, or these introductory or preliminary relationships will give you an idea of the direction or strength before you fit a model. Significant single relationships could lead to covariates, and then you'll also be aware of any changes in direction or changes in strength of relationships when you fit a model. Remember, a strong positive relationship that becomes a strong negative relationship in a model in the presence of other covariates is an indicator of collinearity. If you have very, very wide confidence bounds, when you look at a single relationship and it looks narrow and then you put it in a model and they widen, that's also issues with your variability or collinearity. So doing the preliminary work will really help you in interpreting the model when you get to it. So here's what a table would look like for this data to describe the sample. We needed to indicate that there were going to be differences by gender. and that was going to play into our final analyses. But you can see here that we have proportions, means and standard deviations, medians and IQRs all in the same table. So you don't need to create separate tables for means, for continuous or categorical. You can have them all in one table. Just be careful about how you present it. Then keep track of all the models fit. Tables are very helpful in keeping track of fit statistics. Make sure to check your assumptions of every model. Anytime you change covariates, you need to recheck your model assumptions. Justify your model selection. So if you're using adjusted R-squared, AIC, BIC, log likelihood, whatever, if you're doing direct model tests, just make sure that you keep track of that so you can justify the model. And then make sure you interpret all covariates. The answer to the covariate isn't significant or non-significant, and it certainly isn't the parameter estimate, especially if you did factor effects coding, where the difference between males and females would be double what the parameter estimate is. So you're not reporting parameter estimates when you're reporting results to a lay population. You need to interpret for every change in this level of the covariate, then the outcome changes by this much. Do not leave the interpretation up to the reader. Because you could use factor effects or mean cell or reference cell coding, the parameter estimates are meaningless unless you interpret them in the context of the variable. Here's an example for a figure that tells you that pictures really are worth 1,000 words. The left bar, that's the darker colors, is the proportion of people that reported a doctor visit in that age group. The right bar is the proportion of people that reported an MRI in that age group, and this is in the prior 6 months. And so you can really see that it would be next to impossible to put this in a paragraph or in a table and demonstrate what it is that you really wanted to demonstrate, which is that we're seeing a higher proportion of people seeing the MS doctor at every age compared to an MRI. Now the MRIs become less and less likely in the time frames. So these are the time frames from the last 3 months all the way up to several years. The figure is very helpful, but you'd want to write up the methods based upon your results using the notes that you had, and that would be listed here. So main effect, ordinal logistic model, utilized for each type of healthcare visit, adjusting for gender, current MS type, age, duration of disease, disability levels, medication use and employment. And then a note here about income and employment, because they're highly related. We only used employment. And then you'd want to write up the results. And so here's a very straightforward list of the results with the figures that were referenced. And I will post this poster for you to see. And then a lay description. So this description is useful in terms of what's statistically significant. This description is useful in terms of what it means. More than 2/3 of people have seen their MS doctor in the prior 6 months, but less than half report having had an MRI in the same time frame. Younger participants, females, more recently diagnosed, reporting a relapse, or currently taking DMT were more likely to have had a recent visit of either type. This or is really important here. If it were and, then that would mean younger and female and recently diagnosed, and so you'd be conditioning. This is not and, this is or. So this is for each individual variable. They're all more likely to have recently had an MS doctor visit or MRI. And then there's some sort of more general, we're relatively consistent across all disability levels, and lower disability levels were highly associated with more MRIs, perhaps reflecting more recent diagnosis or relapsing activity. So that's an example of a lay description in addition to the prior statistical significance, in addition to the prior figure. So all of those come to tell a story. So it's really important to remember to keep very clear notes for your qualifying exam and actually for anything you do. It's very rare that you can go through a long analysis, particularly for a manuscript, and get through it in one sitting. Don't use temporary data files because you'd have to start over and rerun everything from the beginning. So if you reach a point where everything's been adjudicated and you save your output as a permanent data file, you can just pick up from that point and move forward. Comment your code meticulously, particularly if you're deleting any observations or if you're making any changes to variables. Print out or save all output as you come through so that you don't have to then look at it again later. You already have it. So if you take a break or you have to stop mid-question, you know exactly what you have done and you will save time when you have to go back to it. And this applies to all analytical work. Up next, we'll take a more in-depth look at that first phase, which is investigating your data. We'll look at data reporting and missing data.